Rate of doing work. Whenever force acts on an object and the object is displaced, work is said to be done on it. For example, when we push a cart, we do work. It can be noticed that greater the displacement, greater is the work done. Similarly, greater the force, greater is the work done. This shows that the work done depends upon the amount of force and the amount of displacement. Hence, work done is the product of force and displacement when a force is in direction of displacement. If two or more forces are acting on an object, then the net work done on the object is the algebraic sum of the work done by each force separately. For example, when a cart is forced to move on a rough surface, the friction opposes the motion. That is, the friction and the displacement are in opposite direction, and thereby the friction force does the negative work on the cart. And the net work done on the cart is the algebraic sum of the work done by each force, that is, the applied force and the friction force separately. If the applied force and the opposing force, that is, frictional force, are equal, the net work done is 0. Further, when the force is applied at an angle to the displacement, then the work done is the product of the component of the force in the direction of displacement and the displacement itself. It can be noticed that if the applied force and the displacement are perpendicular to each other, the work done becomes 0. So, work has nothing to do with the amount of time during which the force acts to cause the displacement of the object. Sometimes the work is done very quickly and other times rather slowly. For example, a rock climber takes unusually long time to elevate his body up a few meters along the side of a cliff. On the other hand, a trail hiker might elevate his body to the same height in a short amount of time. Both the people might have done the same amount of work, though the hiker does the work in considerably less time than the rock climber. The quantity that has to deal with the amount of time during which the force acts to cause the displacement of the object is known as power. In other words, it is a measure of the speed with which work is done on a body. Thereby, power is the rate at which a certain amount of work is done. Hence, the hiker has a greater power than the rock climber. Here, one can see two lifts rising up in two multi-storied buildings separately. One is faster than the other. However, both the lifts are doing the same amount of work. The faster lift is said to have more power than the slower one. Power of an object is calculated by finding the ratio of work done by an object to the amount of time taken to do the work. For an object in linear motion, the change in the kinetic energy of an object is equal to the net work done on the object. Similarly, if an object is raised to a height, the change in its potential energy is equal to the amount of work done on the object. Whereas, if the object is allowed to fall from a height, the change in its potential energy is equal to the amount of work done by the object. In other words, the energy spent or consumed by an object is the capacity of the object to do work. Thereby, the energy spent or consumed per unit time is called power. For example, when a boy climbs an inclined road, he would be more tired while running instead of walking. Here, the change in energy to overcome the gravitational force, that is, his potential energy, is the same, but the rate at which the energy is transformed or the work is done is different. It is clear that lesser the time, more is the power. In general, power is the rate of doing work, and the power is required to produce a constant speed against an opposing force such as gravitation or friction. Therefore, it can also be measured as the product of the applied force and the velocity. Similar to work, power is a scalar quantity, and its SI unit is watt, named after the British engineer James Watt, who developed the first steam engine. An object is said to have a power of 1 watt if it can perform 1 joule of work in 1 second. Other units of power are milliwatt, kilowatt, megawatt, etc. 1 milliwatt, which is 1,000th of 1 watt. 1 kilowatt, that is equal to 1,000 watts. 1 megawatt, which is equal to 1 million watts. Whereas, in the British system, the unit of power is horsepower, which is equivalent to 746 watts. It was James Watt who compared the output of a steam engine with the power of draft horses. The story behind this is that James Watt was working with ponies lifting coal at a coal mine. He was interested to measure the power available from one of these animals. He found out that on an average, a pony could do 22,000 foot-pounds of work in a minute. He also estimated that a horse could do 50% more work than a pony. In this way, he estimated the measurement of horsepower as 33,000 foot-pounds of work in 1 minute. That is equal to 550 foot-pound per second. In MKS system, it comes out to be 746 watt. For understanding the concept of power, let's try some problems. In the given problem, measure the power of a kitchen blender if it can perform 3,960 joules of work in 20 seconds. Here, quantity of work done and the consumed time are given. Therefore, by using the relation for power, it can be measured as 198 watts. In this problem, a man pulls a bucket of water of mass 15 kg from a well, which is 20 meter deep in 25 seconds. Let's calculate the power used by the man. Here, mass of the bucket is 15 kg and the depth of the well is 20 meter. In pulling the bucket of water, the work done by the man is stored as the change in its potential energy, which is equal to 3,000 joules. Since this amount of work has been done by the man in 25 seconds, therefore, power used by the man comes out to be 120 watts. See another problem in which a man having mass 60 kg climbs up 60 steps of stairs in 2 minutes. If each step is 25 cm high, measure the power used in climbing the stairs. Height of one step is given as 25 centimeters. Therefore, the total height covered in climbing the stairs of 60 steps is 15 meters. Since the work done by the man in climbing the stairs is against the gravity, therefore the potential energy is used, which comes out to be 8,820 joules. Further, the time taken in climbing the stairs is 2 minutes, that is 120 seconds. Hence, the power comes out to be 73.5 watts. Let's try another problem. Calculate the power of a water pump which takes 60 seconds to raise 240 kg of water to water tank placed at a height of 25 meters. Since pumping the water from the ground level to some height is the work done in carrying the same mass to the given height and hence equivalent to rise in the potential energy, which comes out to be 58,800 joules. Since the time taken by the water pump is 60 seconds, therefore the power of the water pump is 980 watts. Let's do one more problem. In a bullock cart, the bull exerts a pull on a cart of 600 Newton, so that the bullock cart moves with a constant speed of 72 km per hour. Calculate the power developed by the bull and also find its equivalent in horsepower. Here, the force exerted by the bull and the speed of the bull were given as 600 Newton and 72 km per hour respectively. First of all, convert all the given quantities in the same unit. Since power can also be measured as the product of the applied force and the speed, therefore, the power exerted by the bull comes out to be 12 kilowatt. Further, 1 horsepower is equal to 746 watt. So, the power of the bull is equivalent to 16.09 horsepower. While moving a load against the frictional force, some of the energy is converted into heat, some into sound, and the rest of the energy moves the load. The heat or the sound energy is lost to the surroundings. That is, whenever energy of a device is used to do the work, some of that energy is always lost, and the percentage of the energy that is transformed to a useful or desired form of energy is called the efficiency of that device. More is the efficiency of a device, less is the wastage of the energy. In a water pump, energy is supplied by the pump is utilized in pumping up the water, and some energy is wasted due to the friction of the pipe. That is why when we touch the water pipe during the pumping of water, it appears to be hot.